Hello again. So, graphs have peaks and valleys, and in this video, we're going to discuss finding those peaks and valleys, culminating with something called the first derivative test. So, when I talk about peaks and valleys, maybe we have a graph that looks like this. And I mean, I'm thinking of this as a little mountain range, and this little mountain here has a peak. And this little mountain here has a peak. And this little valley here has a nadir. I'm not quite sure what word is appropriate, but it has a little minimum. Um, and these are called relative extrema. And we also talk, about relative maxima and relative minima. And I mean, these are the same thing. Extrema is just how we collectively talk about these concepts. And the word relative, we have two relative maxima in this graph, here and here. And the word relative is being used because this isn't actually a maximum, right? A maximum is a maximum, just like in everyday English. It's a maximum value. And this is not the biggest the graph gets. We get above it. But it is a peak. It is the top of a hill. So points like that get called relative extrema. It's a relative maximum. And the goal we'll state for this video is to find relative extrema and to classify them. By classify, I mean we have three relative extrema in this picture. Two of them are relative maxima. One of them is a relative minimum. A bit of alternative vocabulary. Sometimes you'll see a local max and a local min. And these are just two different ways of talking about the same thing. It doesn't matter which you use. So how do we find these? Well, a function is increasing when the first derivative is positive, and it's decreasing when the first derivative is negative. So you look again at this picture, and where this function is increasing, the first derivative is positive. So it's positive. This function goes up, then it goes down, then it goes up, then it goes down. The derivative is positive on the first interval where it's going up. It's negative on the second interval where it's going down. It's positive on the third interval where it's going up. It's negative on the fourth interval where it's going down. And sometimes the derivative is zero. And the derivative is lines have slope zero if they're horizontal. The derivative is zero when the tangent line is horizontal, which turns out to be at the first local maximum, at the local minimum, and then at the second local maximum. And this picture gives us pretty much all the tools we need to find local extrema. We'll state a definition. C is called a critical value of the function if f prime of c equals 0 or f prime of c does not exist. So in the picture I just showed you with the three relative extrema, all of those occur because of case A. At each of these 3 points, the tangent line is horizontal and the derivative is 0. What this second option is doing, I mean, we can very easily just draw a picture. We can draw the absolute value, and we see that the absolute value does have a minimum, but the minimum is a corner, so the derivative doesn't exist at that minimum. And I mean, looking ahead a bit, the reason we've stated this definition is the following. Local extrema can only exist at critical values. So, in terms of accomplishing our goal of finding and classifying local extrema, step one has to be to find the critical values. If we've accomplished that, we're halfway there. We're maybe more than halfway there. So for example, let's let f of x be x cubed minus 5x squared plus 1. And let's find the critical values. Our ultimate goal is going to be to find local extrema, but to start with, we'll just find critical values. Well, we take the derivative, 3x squared minus 10x, and we set it equal to 0. You know, there are two ways a critical value can exist. In the vast majority of problems, critical values come from case A. Critical values come from the derivative equaling zero. Like here, this is a quadratic. A quadratic is always defined. There is no possibility that the derivative doesn't exist. So if there are any critical values, it has to come from this being equal to zero. And this is a quadratic, but I selected it to work out well and not require the quadratic formula. We can pull out an x. We get x times 3x minus 10. We set that equal to 0. The zero product property says if you're multiplying two things and you're getting 0, then one of the things you're multiplying has to be 0. So we have two critical values, x equals 0, x equals 10 thirds. And we don't know anything about these. That is, are these minima? Are these maxima? Is one a min and one a max? Maybe they're neither of those things. But if f of x has any critical values, it might not, but if it does, they are at 0 and or 10 thirds. These are the only places where, what am I saying? Good heavens. Any local extrema. If F definitely has critical values, we just found them. But if it has any local extrema, they are at 0 and or 10 thirds. So we're like 9/10 of the way there. If our goal is to find local extrema, but the question, of course, remains, how do we know whether these are local extrema? And if they are local extrema, what kind of local extrema are they? I mean, that is to say, well, what I've already said. Are they maxima? Are they minima? Maybe one's a max and one's a min. We want to be able to classify these. And because you have, I trust, already done the reading and seen the result, and we're just reviewing with this video, I'll dive right in and create a sign chart. So remember, A sign chart is a number line with the critical values marked off on it. 0 and 10 thirds. And we create a sign chart as part of the first derivative test to answer the question we stated and to classify the critical values. And I mean, this is review, but maybe I'm going in a kind of weird order. So maybe before I remind you about sign charts, I'll remind you of the first derivative test, which says that a critical value is a local extrema if and only if the derivative changes sign at the critical value. And we can say more than that. If the derivative goes from positive to negative, it's a local max. If it goes from negative to positive, it's a local min. And if I search back through my notes and I find the graph we started with of the fourth degree polynomial that goes up, down, and has three relative extrema, we can see that. From positive to negative, this is a local max. From positive to negative, this is a local max. From negative to positive, this is a local min. Now, here it's all very well because we have a graph. If we don't have a graph, then how do we know whether the derivative, whether the derivative is changing sign? How do we know whether it's going from negative to positive or positive to negative? Now we create a sign chart. A sign chart is a number line with the critical values marked off on it. So for this example, 0 and 10 thirds. And we use the derivative to construct the sign chart. And we use the following statement. F prime can only change sign at a critical value. And we know what the critical values are here. We've written them on the number line, 0 and 10 thirds. These are the critical values. These are the only critical values. So that means that, for example, between 0 and 10 thirds, the derivative can't change sign. The derivative can only change sign at a critical value. And there are no critical values between 0 and 10 thirds. So it's always positive or it's always negative. What's a number between 0 and 10 third? Um, 1. 1 is in this interval. Go back to the derivative. F prime of 1 is 3 minus 10. It's negative 7. The 7 doesn't matter. The negative sign matters. The derivative is negative at a point in this interval, so it's negative at every point in this interval. Now let's look at the interval of values greater than 10 thirds. So 10 thirds is what? 3 1/3. So 4 is a number in this interval. So's 5, so's 50, so's 500. The specific number I use doesn't matter. I just pick a number in this interval and I go and I look at the derivative and let me see. 16, 32, 48 minus 40. The number doesn't matter. This is positive 8, but the 8 doesn't matter. The positive matters. This is positive somewhere in this interval, so it's positive everywhere in this interval. And there's only one interval left. Look at a number that's less than 0. Look at -1, for example. F prime of -1 is 3 plus 10, 13. Again, the detail, the 13 doesn't matter, but 13 is positive. The positive matters. And this is a sign chart. And now we can see that at 0, the derivative goes from positive to negative. So 0 represents a local max. At 10 thirds, we go from negative to positive. So this is a local min. And that's the first derivative test.